Yeah, I put them on. So we are starting higher level integration, starting with integration by substitution. This is a technique that's used when the chain rule happens, and you recognize the chain rules happen. Can you undo it, even if it isn't pretty? So sometimes chain rules are pretty. And this was a question you did in first semester in your notes with Mr. LaFrance. You were like, if this was the derivative, what equation did you start with? So someone did the derivative, got that as the answer. What was the original question? Can you see that it would just be this to the exponent of 5? And of course, now that we've done integration, we're like, oh, there could have been a plus c. But if you did the derivative of this, you would have the chain rule because you have a function inside of another function. Oh yeah, we didn't do that last question. Let's go back and do that one. Right? I asked you guys to do that one, to try it. I'll give you the answer here. So, car is traveling on a straight road velocity. Okay, and you got the graph, right? The graph was given to you. So you could figure out just geometrically what each of those areas are, and that's your accumulation of change. This is your graph of acceleration. So if you want to find a of 15, we've got that point on our graph at -20, no problem. If you want to find the velocity of 15, that will be what your initial velocity was, plus your accumulation of change from your rate of change. So from 0 to 15, if we go through this, we see that this change is 150 minus that 50, which is just 100. We were told that we had an initial velocity of 80, and from 0 to 15, the change was 100. So your new velocity is 180 feet per second. I think that's faster than I can run. Then part B, at what time other than 0 is the velocity 80 feet per second? So we started at 80. The area under the curve would add all of your accumulation of change. Do you notice that at 20, the 150 that's added gets canceled out with 150 that's minused? So at 20, you will be back to 80 once again, because your accumulation of change will have canceled out. What is the car's absolute maximum and absolute minimum? Well, it starts at 80, then you add 150, then you subtract 250, then you add 25 again. Am I scrolled too far, too fast already? Are we okay? A little bit? Okay. I'll wait a little bit. I'll wait. Okay, so if you want to use the extreme value theorem, you would have to check endpoints, and wherever the acceleration changes sign. So we know our one endpoint is at 80. Changes sign at 10, that's 230. Changes sign again at 30, that's negative 20. And the other endpoint at 35 is at 5. Of those ones, using the extreme value theorem, the biggest one is 230. The smallest one is negative 20. So the extreme value theorem says on an interval, you will get an absolute maximum, either at its endpoints or at one of its critical points. And you find the critical points by setting the derivative equal to 0. Well, the derivative of velocity is acceleration. And so we just need to see where our acceleration graph is equal to 0. The exam really likes accumulation of change questions because they can ask like extreme value theorem in context. Yes.
How does this relate to the extreme value theorem?
So you want to find an absolute minimum and absolute maximum. So that is in itself extreme value theorem, finding a maximum. We have an interval with endpoints. So extreme value theorem says on an interval of endpoints, your extreme value will either be at the endpoints or at a critical point in the middle. So if I have some graph, if this is my velocity graph, right, my velocity graph from A to B goes like this. I have a critical point here, an endpoint here, and an endpoint there. The one critical point happens to be our maximum, but our minimum happens at an endpoint. You could have had, let's say I draw a second graph. I have two critical points. An endpoint there, an endpoint there. Can you see the one critical point's a minimum, but my endpoint is actually the maximum, not the critical point. So your extreme value theorem says you have to check all of your endpoints and all of your critical points to make sure you know which is your maximum and which is your minimum. So that's what we did here. We looked at our graph, and you see that on your graph at 10 and 30 is where your acceleration is 0. Acceleration is the derivative of velocity. So those are your critical points. And we check our endpoints. And we find our values that way. Okay. Everybody good? So now we can go back to where I was starting. Integration by substitution. And if you were to integrate, so we're going to get this same question, but it's going to look like this. I don't want to find a way that we can figure this out easily. And the technique that we're going to learn is called integration by substitution. What we do with integration by substitution is we take out some of the complicated stuff so that the derivative is easier to do. Okay? For example, what looks easier to do? This integral or this integral. The one on the right is a lot easier to do. So what we have to do is find out how can we take this complicated one and change it to the simple. Because this integral is just u to the 5 plus c. Okay? I'm going to substitute the 3x squared plus 5x for a u and see what happens. But first of all, how do we know when we want to use a technique of integration by substitution? Can we recognize in a question that the chain rule happened? So in each of these integrals, what I looked for in yellow was where I had an original function and then its derivative happened afterwards. Because that's what happens in the chain rule. When you have a function inside of another function, you do the outside function first, and then you multiply by the derivative of the inside function. So our goal here is to see if we can see a derivative in the equation, and also we're looking for an original function that might be inside of another function. And some of them get a little bit tricky. I would say the first 4 are easier to see. 5 is a little bit harder. 6 and 7 are a little bit easier. And then the last one is a little bit harder again. The last one's actually messed up a little. We're going to have some fun with that one. Everybody done highlighting? We take out our same highlighter. What we're looking for is we are looking for a function inside of another function, and that inside function also has its derivative up here. If this happens, we change that inside function to u. And if we change the inside function to u, we can take the derivative of the inside function, and this feels a little bit like cheating, but we're allowed to do it. Actually feels a lot like cheating. Do you know how du dx is a derivative? Do you know how du dx is like Leibniz notation? Well, in Leibniz notation for integrals, we just sort of pretend it's like a fraction, even though it's not a fraction. Du dx is a derivative. But if we pretend it's like a fraction, could you move the dx to the other side? If it was a fraction, you could. It's not a fraction. We're cheating a little bit here, but it works beautifully. So we'll just sort of ignore the cheating a little bit and just accept it. It's not really a fraction, but it works. Okay? Here's the first one. The 7. I notice the x squared minus 7 is in the power of 4, and the derivative of x squared minus 7 is 2x. And so the first thing I do is I let u equal that inside function. What we're going to want to do is see if we can manipulate the original integral into something that's easier to do. Some of you could possibly do this with mental math, but sometimes there's just too many little tiny numbers and calculations that happen that get you bogged down and screw you up. So the substitution takes away some of that and makes it easier on us. What does this allow us to do? I am going to replace, you see how I can replace, obviously the yellow part with u, but now I can also replace all of this 2x dx with du. And my integral now just looks like this. Super easy integral. Super complicated integral, a little substitution, super easy integral. How do we do this one? Add 1 to the exponent and divide, plus c. And then if you want to, which we do, we substitute that. If you're ever curious if you did an integration right, just take the derivative. Right? How would I do the derivative of this answer? My 5 would come out in front, subtract 1 from the exponent. Can you see if your 5 came out in front, it would cancel with that 5? And you would get x squared minus 7 to the 4, which we have in yellow here. But this would have a chain rule, so we'd also have to multiply by the derivative, which would give you a multiply by 2x, which we have as well. So you can always check by taking the derivative to see if you've got it right. Substitution, using this technique, is kind of an art because you have to analyze the question and recognize original functions and derivatives built in. So for example, it looks complicated. When things look complicated, you go, okay, well maybe I could use substitution. I have an ln x inside of a power of 4. So I have a function inside of another function, and the derivative of ln x is 1 over x. So it makes me think I should make u ln x, and then my derivative, du dx, is 1 over x, which means if I got du by itself, it would be x to the minus 1 dx. So all of this in purple, all of this here in purple gets replaced with the du. The ln x gets replaced with the u, and we have the exact same question as the last one. But I'm pretty sure when you looked at A and B, you wouldn't say, oh, it's the same question. They don't look at all the same initially. But add 1 to the exponent and divide, substitute back in, and there's our integral. The next two I'm going to get you to try. And then we'll do E together. There's our inside function, so we let u equal that. Our derivative matches up nicely. Then du dx. Cube root is to 1/3. So especially when things are fractions, It would be hard to try to manage all of that in your head at once. So the substitution makes that easier for us. And here's D. So the derivative of sine is cos, and the derivative of cos is negative sine, so it's like, which one should you make u? Do you see that sine is inside the function e? That's what's telling you should let u equal sine x. Du dx is cos x. Things match up nicely to be this. The derivative is that. And we can substitute that. And we'll leave E for tomorrow.